Good morning, and for those visiting our great state, welcome to Delaware. I'm Congresswoman Lisa Blunt Rochester, and I'm proud to join you for your annual National Academy of Engineers regional meeting, hosted by the University of Delaware and Chemours. Let me begin by thanking UD President Dr. Dennis Asanis, College of Engineering Dean Levi Thompson, and Dr. Yushan, President of UD Center for Clean Hydrogen, for hosting this event on campus and for your leadership. The work being done at the University of Delaware is cutting edge, innovative, and transformational. I also want to welcome NAE President John L. Anderson, along with all of the NAE members present here today. As someone who comes from a family of engineers, my sister, an industrial engineer, my brother-in-law, a nuclear engineer, and my late husband, Charles, was a mechanical and aerospace engineer and a blue hen, I recognize the talents, skills, and expertise you bring to your work and respective fields. You enable us to solve the greatest challenges we face and improve our quality of life. Which leads me to our planet and the opportunities to save it. As you know, hydrogen is the fuel of tomorrow, and it can be used to power cars, trucks, planes, and ships, making transportation of passengers, products, and produce cheaper, quicker, and faster, and safer. It is critical that together we work towards a transition to hydrogen in order to decarbonize multiple sectors of our economy. And we're going to achieve that goal in an equitable, just, and sustainable way. That way, it benefits all of us, not just some of us. And we will do this working together because we all have a part to play in bringing this to life. The transportation sector accounts for about 1/3 of U.S. carbon dioxide emissions. So by investing in hydrogen as a clean energy source, we can limit the use of greenhouse gas, meet our collective goal of cutting carbon pollution in half by 2030, and reach net zero emissions by 2050. I'm proud of the work we are doing to encourage the transition to hydrogen. I've been proud to champion the bipartisan infrastructure law which President Joe Biden signed. One of the most significant products of that law is the Mid-Atlantic Hydrogen Hub, also known as MACH2. In Delaware, we have the skilled workforce and the existing energy infrastructure, in addition to our strong industrial presence and positioning in the region. We are a leader, and we are a leader in clean energy. As Delaware's former Secretary of Labor and the founder and co-chair of the bipartisan Future of Work Caucus in Congress, I'm laser focused on connecting people to the jobs of today and the jobs of tomorrow. To that end, the MACH2 framework is expected to create an estimated 20,000 good-paying clean energy jobs, including union jobs. Hydrogen is a win-win-win. With all of these partners at the table, in Delaware and around our region, we can do this. And as we work to make decisions about our transition to hydrogen, I look forward to continuing our efforts in partnership with everyone at the University of Delaware and across the NAE. Thank you again for all you do, and I wish you all a successful regional meeting.
And with that, I would like to welcome the President of Advanced Performance Materials for Chemours, Gerardo Familiar.
Thank you, Tim. What a great day, right? It's been great presentations, and it's a great opportunity for us to talk, to meet, and to discuss all of the things that are important for the world. So, good afternoon, everyone, and welcome. Thank you all for joining. And special thank you to the National Academy of Engineers, the University of Delaware, and all of the partners here today. We're all here today because we know that the world needs innovation and solutions for a sustainable, clean energy future. And we know there is no path to net zero without hydrogen. And it's these partnerships across industry, academy, and public sector that are enabling the hydrogen economy and the solutions that we need to reach the climate goals. We have great presentations coming up, but first, I would like to share a little bit about what Chemours' contribution into the hydrogen economy is doing. Let me just start by sharing that our Nafion materials, membranes, are the heart on the PEM electrolyzers to produce hydrogen. Our materials are also in the heart of the fuel cells that uses that hydrogen in order to have mobility solutions. Fun fact, the Nafion products, the Nafion technologies, were invented in the 60s as part of a NASA space program and started to be produced in the United States in the 70s in North Carolina. We still have that facility that is producing these products in the United States. Chemours is positioned to make a significant contribution to the hydrogen economy through the investments on technology, responsible manufacturing, and decades of research. We continue investing in new capacity. We have announced big investments in new capacity for the hydrogen space to make sure that supply chains have enough materials to enable the hydrogen economy. But there are challenges ahead. The growth of the hydrogen market and achieving the bold goals outlined by the administration and our friends of the US Department of Energy requires policies that support scaling the pipeline at the speed necessary to drive parity in the cost of hydrogen. We are committed to support future-oriented policy programs aimed at fostering the energy transition. The future of hydrogen depends on strong partnerships, and that's been the focal point of our strategy at Chemours. We're not only a leading supplier of membranes, we're also proud project partners in the center of clean hydrogen here, which will drive innovation to bring down the cost of hydrogen and increase efficiencies. We're really excited to be partnering with the University of Delaware, with the US Department of Defense, with Plug Power, NREL on this center. Also, last month, the DOE selected 2 Chemours applications for grants. Chemours and our partners will use those grants to develop next-generation PEM water electrolysis for a domestic hydrogen economy supply chain, and to establish a consortium of recycling for PEM electrolyzers and fuel cells. Fostering these partnerships, it's a pathway to a more sustainable future. Chemours is committed to the growth and success of our partners, our customers, and the hydrogen economy. If we continue to work together and build strong private-public partnerships, then we will make clean hydrogen a reality and help build a more sustainable future. I want to thank you all for your commitment, for your partnership, and let's continue working together on enabling the full potential of clean hydrogen. With that, I'll turn it over to the presentations, but thank you very much.
Thanks, Gerardo. So for our first presenter,
Could I ask a question?
real quick.
Yeah, absolutely.
Maybe after. Oh, my recollection is the largest electrolyzer that I'm aware of is like 5 feet by 12, Newark, used maybe. The form factor was limited by the width of the web. Is there any idea of going beyond, I don't know, it's like 4 feet or 5 feet, beyond that, so that a larger size form factor could be possible?
So what I can share is that as we speak, we're currently working with different companies that are working on the design for those membranes and for those CCMs and MEAs. And what we're doing is working together on what are the needs that are required. So we are building new capacity that is going to be coming of ionomer. That's going to be ionomer polymer, and then for membrane. And this is going to give us much more flexibility on designs that are required. But the key thing that we need to be thinking about is what do we really require to have a better performance, to reduce the cost of producing hydrogen, but also trying not to have many things that are very different, equipment by equipment, because we need to get to a place where we standardize things, because that's going to help us to reduce cost on the design of these equipments. Thank you.
All right, thank you. So our first speaker of this session is Dr. Andrew Park of the Chemours Company. So Andrew is a senior principal engineer. He has over 15 years experience in the manufacture and evaluation of membranes and membrane electrode assemblies for the hydrogen fuel cell and water electrolysis. Currently, Andrew leads the effort in Nafion membrane and ionomer research and development at Chemours, and has been the principal or co-principal investigator on 3 Department of Energy programs aimed at next generation materials and hydrogen applications. So with that, I'll welcome Andrew.
All right, thanks, Tim. And thanks, everybody, for being here this afternoon. As mentioned, I'm Andrew, and I'm here to give a little bit of an update on the work we're doing within our Nafion division to engineer membranes for the proton exchange membrane water electrolyzer. So I think you guys have probably heard a lot about Chemours by now, but if not, we comprise 4 divisions, one of which is our Titanium Technologies division, which includes our TiO2 paint additive. Thermal and Specialized Solutions refers to our refrigerants division, of which brands you might be familiar include Freon and Opteon, which is our new low greenhouse gas potential refrigerant. We also have a Chemical Solutions business unit comprising specialty chemicals, but I'm here to follow up a little bit on Gerardo's statement under the Advanced Performance Materials section. So Advanced Performance Materials, or APM, comprises a lot of brands that you're probably familiar with. The lead among them is probably Teflon, our PTFE line. And of course, Teflon goes into a lot of the applications that drive our everyday industry, such as cars and our homes and smartphones, but also heavy industry like semiconductors. Other brands you might be familiar with include Viton, perfluoroelastomers, and Krytox lubricants. But I am here today to talk about Nafion, which, as mentioned, has a special role in the use and manufacture of clean hydrogen. So Nafion is a membrane, or can be used as a membrane, in the proton exchange membrane, or PEM, water electrolyzer. So as mentioned, electrolyzers split water using electricity into hydrogen and oxygen subcomponents. And the PEM electrolyzer is relatively unique in that it uses a solid polymer membrane as its electrolyte. And so this solid polymer membrane, the proton exchange membrane, is used to conduct the protons generated at the anode during water splitting to the cathode, where they are reduced to form the hydrogen gas. So there's a lot of benefits associated with having the solid polymer PEM membrane to do the water splitting. These include the ability to dynamically follow the load into the electrolyzer. So for example, if electricity is cheap or the hydrogen demand is very high, we can run these PEM electrolyzers at full power. But when electricity is expensive, or maybe you don't need so much hydrogen, you can actually dial down the output of these PEM electrolyzers pretty easily. And you can cycle them on a pretty fast timescale, following the demand or need for the hydrogen, which is somewhat unique to this PEM type of electrolysis, where other types are more constant. In addition, with that solid polymer membrane, it enables stack users to some degree, compress the hydrogen at the outlet of the stack, which helps to reduce the compression steps required to get the hydrogen up to the pressure required by the end user. In addition, PEM electrolyzers have the highest current density of any electrolyzers on the market, which allows them to have a relatively small footprint, perhaps enabling distributed generation of hydrogen rather than big centralized facilities, although those are also possible. And then, of course, PEM electrolyzers enable a very high gas purity, and they've been demonstrated in the marketplace now for several decades, and so we can trust that they have the durability required to enable some of the applications that Kathy mentioned, like 50,000 plus hours of hydrogen generation. Now, what we do need to do as a community, we're not done with the engineering of the PEM electrolyzer. There's a lot of work that needs to go on to improve the design of these stacks, in particular the subcomponents that go into generating this hydrogen. And so that's what we use Nafion for. Helpfully, Craig already introduced the concept of these Nafion-type ionomers, which again leverage a combination of mechanical strength from the TFE component within the polymer, but also leverage a percolating water channel network, which when tuned between the ratio of these two monomers, allows a very mechanically robust membrane to be formed while still allowing these nanochannels to conduct protons from one side of the membrane to the other. And so you'll find devices containing Nafion membranes at the heart of many electrochemical devices, and I'll get into that here again in a second. But it bears mentioning that Chemours has been manufacturing Nafion for many decades. As part of DuPont, Chemours invented Nafion. And so we have a deep backwards penetration into the supply chain that is also reasonably unique. So we go all the way back to raw materials to make the monomers that go into Nafion. So we make those monomers. We then take the monomers, polymerize them to get the Nafion polymer. And then we use the polymer to make Nafion membranes and dispersions. Owing to our significant history in the commercial manufacture of this polymer, we have the capacity to enable the scale up of membranes utilizing this polymer to support the growth of the hydrogen economy. So it bears mentioning also that due to this deep backwards penetration into the supply chain, we have several opportunities to incorporate end-of-life materials back into the Nafion supply chain. And I'll talk a little bit more about that at the end of the presentation. But as the market grows and as we make more PEM electrolyzers, it will be necessary to take the Nafion at the end of its life and return it back into a productive piece of the supply chain. And we have several opportunities to incorporate that end-of-life Nafion subject to what's best for the supply chain. Maybe the last piece in general, I want to hit on responsible manufacturing of fluoropolymers. This is extremely important, and Chemours has a lot of value and emphasis on manufacturing these fluoropolymers safely at our facilities. One example of that is a greater than $200 million investment that's gone into a state-of-the-art thermal oxidizer facility at our Nafion production plant in Fayetteville, North Carolina. And that thermal oxidizer is capable of essentially eliminating any sort of airborne fluorinated components to the atmosphere. So it's one part of our commitment to ensuring that the manufacture of these fluoropolymers is done safely and responsibly. It should be noted also that there has never been at any time a use of fluorinated small molecule surfactant during the polymerization of Nafion. Beyond the fluorinated components, there's a significant reduction in greenhouse gases associated with our corporate responsibility goals, not only at Fayetteville, but also at plants throughout the US and the world. So again, a significant effort is being placed on responsible manufacturing at Chemours, and there's certainly a lot more information about this in other venues. So before I get into a little bit of the technical portion of the talk here, I thought it might be helpful to zoom out a little bit and talk about other membranes utilizing Nafion that exist in the market. So in the electrochemical space, there have been two technologies that leverage membranes containing Nafion that have had decades of optimization poured into getting these things into the places where we need them to be. So for example, the hydrogen fuel cell membrane is a very thin membrane. It's at current generations, maybe between 8 and 15 microns thick. And it leverages a dispersion casting process where a liquid dispersion of Nafion is coated onto a substrate and then dried in an oven to form a film. But then chloralkali membranes, which are, again, a Nafion-containing membrane, are extraordinarily different. They're an order of magnitude or more thicker at 200 microns or above, and they're produced by an extrusion casting process where we take a melt processable uncharged precursor to the Nafion and extrude it into a freestanding membrane, and then subsequently convert it into the sulfonic acid proton conducting form. And so these membranes, looking at them, they look extremely different. But if you take a step back and look at them a little bit more generally, they both contain kind of the same strategies in order to get them to their optimized place. They each use a reinforcement intended to improve either the durability and or the handling of these membranes in use. And they contain additives that have some sort of beneficial application, such as a radical scavenger, as mentioned by AJ, for fuel cell durability, or in chlor-alkali, they can facilitate gas release at the surface. So again, it's not just Nafion that's making these membranes work. It's a composite structure utilizing Nafion in context of also a reinforcement and an additive strategy in order to realize the best membrane that we can use. In electrolysis, we're not there yet. So traditionally, over the last couple of decades, electrolyzers have used, instead of that composite approach, a homogeneous Nafion membrane. And these, compared to what is ultimately necessary, are probably over thick. And that high thickness contributes a proton transport resistance into the electrolysis application. And so it means that you need more energy to make a given amount of hydrogen. And so our vision here for kind of the next generation of optimized electrolyzer membranes, what it is going to look like once we get that engineering into it, is a little bit more like the fuel cell and the chlor-alkali membrane. So it's going to be thinner. It's going to have a reinforcement to improve mechanical properties, improve durability, and it's going to have some additives that improve the durability and safety of these membranes. So it's not exactly clear to me what the ideal structure is going to look like. If you go back to that last slide, you had one production pathway to make a fuel cell membrane, very thin, dispersion casting type process. Then you have an extrusion type process to make the chlor-alkali membranes. And the envisioned thickness of these water electrolysis membranes is kind of in the middle. And so it's feasible to utilize the lessons from the fuel cell membranes to make the next generation of electrolyzer membranes. But it's also feasible to maybe utilize the lessons from chlor-alkali. And Chemours is well positioned to do the optimization work here because we're about the only company in the world that has the experience and the manufacturing capability to do both. And so we have active programs in different ways to look at getting to the optimum electrolyzer membrane. But what I'm going to talk about here is one of those approaches. So this is going to be summarizing a project that's just ended, that was funded by the DOE from March 2020 through the end of last December. And so this was a project that I led with Siddharth Kamini Babu at Los Alamos National Lab, with other extremely important contributions from NREL and Lawrence Berkeley, that aimed to manufacture a thin, reinforced membrane with durability enhancing additives to aggressively chase high performance while also ensuring durable and safe operation. So to kind of explain the point of why we want to do this here, I wanted to show a few polarization curves. Can't stop me from presenting all data. So, most people are either extraordinarily familiar with this or maybe have never seen this in their life. So this is a polarization curve looking at the relationship between the electrical potential in the electrolyzer versus the current density that we're getting out of this. And the current density is directly related to the amount of hydrogen production. And so the ideal polarization curve would have a lower cell voltage at a given current density, which is directly proportional to the efficiency of the electrical input that we're using in the electrolysis unit. And so you can see here, this is a membrane called N117. It's 175 microns thick. And as you go down in thickness, you can see the polarization curve goes down with it. And so that's taking these membranes and making them thinner. You're taking the proton transport resistance associated with getting protons from anode to cathode and shrinking it. And the impact is dramatic. So you can see that the efficiency of the overall system is increased here by 10%, simply by membrane changes. And so this is an example of why we need to improve the membrane in these proton exchange membrane electrolyzers. But it's not just as simple as making the membranes thinner. As you decrease the thickness of the membrane, its barrier properties for hydrogen crossover get worse. So what you're looking at here is the hydrogen content as measured in the oxygen stream as a function of current density. And so as you see here, at low current densities, you're producing less oxygen, and so there's less oxygen around to dilute the crossover hydrogen. And for a relatively thick membrane shown in yellow, that's in 117, it may not be the biggest deal, but for thinner membranes, it starts to become a challenge. This line here, 100% LEL, that's the point at which the hydrogen and oxygen mixture becomes explosive, which is bad. And so we want to avoid that amount of hydrogen and oxygen quite strongly. And so the problem is magnified when going to 30 bar of hydrogen pressure. So one of the benefits, of course, is that with the solid polymer membrane, we can compress the hydrogen to get an efficiency gain through fewer compression steps. But without a mitigation strategy, it's very difficult to implement these kinds of membranes. So the benefit of this project is not only engineering membranes, but how do we quantify gas crossover so that we can actually do the mitigation? So one of the highlights here of the collaboration of this project is shown here. This is some work at NREL. And of course, there's a lot of chemical engineering going on this slide, but the simplified picture here is NREL is taking the anode exhaust, this is the oxygen stream with hydrogen mixed in, and diluting that whole thing in nitrogen, such that no matter how much hydrogen is in that oxygen, if we blanket it in an excess of nitrogen, we can run that through a GC and detect what's there. And so, this kind of shows what's going on here. So on the left here, this is the total gas mixture as determined by the GC. As you can see, the H2 and O2 combination is well below 1% in totality. But if you extract out the nitrogen component, you can measure the ratio of H2 and O2 to see what it would be if you didn't have the nitrogen mitigation. And that's where you can safely measure this high hydrogen and oxygen content without actually getting into a dangerous situation. So kind of skipping a few steps here, the way that we've figured out to mitigate hydrogen crossover, not to fix hydrogen crossover, but to mitigate it, is to take what's called a gas recombination catalyst, or GRC, and we incorporate that within the membrane to recombine the hydrogen crossing over across the membrane with oxygen coming from the other side to form water. So it's a relatively simple chemical reaction. Hydrogen plus oxygen goes to water. It's the opposite of what the electrolyzer is doing. But that effectively mitigates the amount of hydrogen that can exist in that anodic oxygen stream, which ensures that these electrolyzers can be operated safely. And so what I'm showing here, this is a lot of membranes that are all kind of clustered at the bottom. This is at 0 bar hydrogen back pressure. And so everything with the GRC looks good at 0 bar, but if you take it up to 30 bar back pressure, which is kind of what a lot of customers and a lot of OEMs want to operate at, and you can see that the differences between different GRCs, different incorporation strategies start to manifest themselves. And so you can go from this yellow, the blue line, which is an unmitigated membrane, no GRC, and you can see that as you increase the efficiency of this mitigation technology, you start to slightly reduce, then more reduce, and then essentially eliminate the amount of hydrogen that you can quantify in that oxygen stream down here toward the bottom. And so kind of zooming to the end of this project after 3 years of work with our collaborators, from a performance standpoint, we were able to engineer a membrane that contained a reinforcement that not only met but exceeded the performance that we saw from that 50 micron membrane from the earlier slide. So we're pretty excited about this because this not only meets but actually exceeds the DOE 2026 target for performance of the PEM electrolysis. So that's reasonably exciting. And then for hydrogen crossover, the new line here is what's in black. This is the amount of hydrogen we can detect in the oxygen stream, both at 0 and 30 bar with our most recent prototype. So we're all very excited about that, But in the spirit of not exaggerating, what you're not seeing here is durability. And for the most part, that's because we don't necessarily have all the resources that we need to do this type of testing. This project, I would say, was early in the electrolyzer optimization push, and it ran into bandwidth issues in terms of simply having the testing to get membranes on stacks and get them evaluated for hundreds or even thousands of hours. So there's a lot of work that needs to continue to be done to optimize not only the membrane structure, but then to prove it to ourselves and to our customers that it's reliable for hundreds, thousands, tens of thousands of hours. So toward that goal, we have a couple of projects, as Gerardo mentioned, that we're extremely excited about. The first one that I want to talk about is this durable high-performance membranes for proton exchange membrane water electrolysis. This is a project that I am intending to lead here for the next 4 years with our partners in Accelera and UD, where we will manufacture a series of membranes and then prove through new protocols and stack testing that they are durable, leveraging fundamentals provided by the Center for Composite Materials here at UD. And then as mentioned earlier, I think this has come up several times now, but the H2 CERT program, of which many of you in the audience are members, this is extraordinarily exciting. So Ben Gold in the audience is the Chemours PI for this work, and it intends to examine routes to reincorporate Nafion at end of life back into the Nafion supply chain. So currently, these MEAs are essentially pyrolyzed to recover the iridium and the platinum catalysts, which destroys the Nafion ionomer, and so it would be far more desirable to find ways to reincorporate the Nafion in some way, not only for the economics of it, but also for the responsible manufacturing piece. So with that, I'll thank this whole list of people, the collaborators at the national labs, and if there's time, take questions. Thanks.
So with that, I think we have time for a few questions.
Hi, my name is Hopkins. I'm at DuPont. Can you lower the potential by using Nafion with a lower EW?
That's certainly possible. That's one strategy that can be done. There's many ways to reduce the proton transport resistance associated with membranes. Of course, there is a practical limitation to lower EWs, and that's a piece of our optimization strategy.
Yeah, Mike McConnell, Holtec. What's driving the pressure? You talked about 0 bar versus 30 bar. Was that just trying to increase the throughput?
So it's really a customer offtake perspective. So often for fuel cell vehicles, for example, the pressure of the hydrogen in the tank is 700 bar. And so taking hydrogen from 30 bar to 700 bar is much easier than 1 bar to 700 bar. So I think it's my understanding that if you go from 1 bar to 30 bar, you essentially take one whole compression step out of the required mechanical compression to get that hydrogen up to where it needs to be. And I think I understand from somewhere that might save up to 4% in terms of the whole overall system efficiency. So it's certainly something that we've gotten market feedback that's desirable, and I think that's a good summary.
All right, Craig?
Yeah, no boy.
Elaborate a bit about the types of failure modes you're going to be evaluating in the new project?
I mean, the failure modes are essentially the big black box of membrane work at this point. And so there's chemical degradation modes, there's mechanical degradation modes. I think Kathy mentioned creep of polymer over time is certainly something we're going to be looking at. And this is all in context of changing iridium catalysts. It's in context of changing porous transport layers. And so there's complex interplays between not only the membrane as it's changing, but also the PTL, the iridium catalyst, that are all kind of going to feed into how these things fail. And so I think that is the key underlying principle of this project that we've got proposed is how do we understand the durability failure mode so that we can actually make these things better.
Should we be looking at the effectiveness of the GRC and make sure that doesn't degrade over time
100%,
as well?
100%.
Last one.
Is there
Yes.
any value in revisiting the Dow chemical membrane, which had those I mean, I don't know what happened to that membrane, but it had some advantages.
Yeah, I think what you're referring to is, yeah, the short side chain membrane. And there's certainly, various ways of structuring that. So Nafion is one example of the, perfluorosulfonic acid that Craig acknowledged, and there are certainly different ways to make membranes. Leave it though.
So Solvay, or Scienco, whatever they're called now?
Scienco, yeah.
Scienco, that they have a
They're
product that's
pursuing
short
it?
side.
All right. Thank you, Andrew. All right, it's a pleasure for me to introduce our next speaker, my neighbor here at Star Campus. Barry Sharpe is the Vice President of Operations for Bloom Energy and the appointed General Manager of the Bloom Manufacturing Center of Delaware. He was responsible to design, build, staff, and launch the facility in Delaware. He has since grown the workforce into a model of lean manufacturing. He has 25 years of experience in automotive manufacturing leadership with both Ford and Toyota. He worked in multiple facilities with Ford Motor Company. He then worked 8 years with Toyota, including becoming the general manager for the last 5 years. He has a lot more experience. I'm going to skip to Barry has a bachelor's in business from Georgetown College. He has a master's in mechanical engineering from Georgia Institute of Technology, and I had to reference that it says while coaching football, so you'll have to make a couple comments on that. And with that, I'll turn it over to Barry. Thanks.
Yeah, that's one of those. Football was very, very good for me, right? So it paid for the whole education. And so being a engineering conference, we're going to tag team with, I'm bringing a couple more engineers up to join me. So if you guys want to go ahead and come up. My background was robotics and computer integrated manufacturing systems was my ME based master's program. These gentlemen, so Charles Walton is a mechanical engineer out of Naval Academy, and he's also a nuclear, a Navy nuke and operated a nuclear facility as well. So he brings a lot of background to us. Charles is our director of engineering for all of engineering and testing at the Delaware facility, and Brian Hadley is a master's of electrical engineering and power electronics, and so that background has served us well. I like to introduce both of these guys and join them in this presentation because they've been a big part of our association with the university here for the last 10 years as well. So we've done many projects that way. So that's kind of how we're taking it on our presentation method. So to start, I'd like to kind of introduce Bloom Energy. So first of all, we are headquartered in San Jose, California. We have both manufacturing and R&D locations in San Jose, in Delaware, and in Bangalore, India. We've grown now to a size of 2023 was $1.4 billion of revenue, and are profitable as a clean energy company for the first time, and very proud of that and very intent on staying that way. We've generated over 20 billion kilowatt hours, all without combustion, and that's important for us. It's part of our foundation, and we've deployed over a gigawatt of electricity in 1,000 installations. 150 of those are microgrid installations. And I think what kind of makes us a clean energy company is three different elements. One is the fact that we don't use combustion in the beginning allows us to create electricity without any of the traditional clean air NOx and SOx components, and so that kind of sets us in the beginning of a clean air mindset. Secondly, on the carbon concept, we implement applications of being able to use hydrogen to generate electricity, and being able to use biogas to generate electricity, and we do that in the field now, as well as a carbon capture element that we provide as well. So we have multiple sides of the current electrical fuel cell process that is clean. And then next, within the capability of generating hydrogen from the same fuel cell technology to create clean hydrogen with either green or pink from nuclear applications makes us a little more crossover into that region as well. Our model is in a distributed electricity mode, right? So we produce the electricity on site, and so we manufacture everything here. So we manufacture in Delaware, we distribute on site. Every product that we have sent to site for the last 12 years, since 2014, has come through the facility that you can see through the window here across the park. It's not still raining, and so the intent is for us to continue to grow in what that process is. The basis of the solid oxide fuel cell platform and the way we've utilized it here is a very flexible system. And so we can generate outputs of AC power, DC power with varying voltages based on the need or the country that's producing. And also we can do load following with flexible current. We also can produce hydrogen. We can produce water, we can produce oxygen. The foundation of this product was created by our founder and CEO, K.R. Sridhar. When he was at the University of Arizona, he was awarded the contract for producing the fuel cell that would go on the manned Mars mission to generate oxygen and water, and that was the foundation. So when the manned Mars mission was canceled, he switched over, went to Silicon Valley, and turned it around and created a situation where you input fuel and create electricity. And so that's the foundation of the product. The inputs can be natural gas, biogas, hydrogen, any form of clean intermittent energy sources, wind or solar, and then the grid. And so that flexibility is what the basis is for our product and our facility. And our lean manufacturing facility that we've created here within Delaware allows us to be able to produce any of these products in any volumes, in any sequence. And that's what's truly remarkable about the lean manufacturing capability and us being able to do that. And so that capability gives us the opportunity to allow Bloom to grow to a gigawatt of fuel cell and a gigawatt of electrolyzer capability in pretty short order. I mean, literally within 6 to 9 months, we can take a large order and we can deliver it on site for implementation. So we have a product. We're ready for the product in to deliver the hydrogen, and we're waiting on and working on the market. So our product right now is solid oxide fuel cell or electrolyzer is operating off of the same platform as the solid oxide fuel cell, and so all of the basic technology and infrastructure cost reductions that we've made, magnitudes of cost reductions over the last 10 years, all feed into our capability of doing the same thing with the electrolyzer. Because it is a high temperature solid oxide fuel cell at around 800 degrees Celsius, it becomes much more efficient than any other form of electrolyzer. So when we look at the chief cost element of of hydrogen, electrolyzer hydrogen, is the cost of the electricity, then the efficiency rating is a considerable impact on what the cost of that end result of hydrogen is going to be over time. It also has a very dependable, slow degradation of efficiency within the market. And so when you put the product in service, the degradation of efficiency is going to be very slow across the solid oxide fuel cell, and that allows us to maintain those ratings. And so we're looking at lifetime cost with the customers that we're talking with, and that's what allows us to be able to project that we can get to a 2 gigawatt per year type capacity in a few years. So the distributed basis is part of what our same mission is within the electrolyzer, and so we're not looking to build facilities, build plants. We're looking to place the electrolyzers. Some of the contracts we're talking about may be 100 megawatts, maybe 20 megawatts, but they're looking for on-site capability. They're looking for operation density, and those are the type of functions that we're working on to be able to make our product much more palatable within business, and then at the same time be able to grow this and remain profitable. And so much of the cost element is what we're looking into right now. And so from that, I will turn it over to Brian to talk more about the technology.
Thanks, Barry. So we've already gone through this a little bit already. I'm not going to go through it too much again because we all sort of understand what how a fuel cell operates. The primary distinction between SOFC and a PEM is really the electrolyte. It's the mechanical structure is very similar. It's a cathode and anode that sandwich a solid ceramic electrolyte in between. In the case of solid oxide fuel cells and electrolyzers, the electrolyte allows the passage conducts passage of O2 ions through at a certain temperature. So once the electrolyte is up to temp, it becomes conductive for O2 ions. When operating as a fuel cell, we supply the fuel cell system with methane, CH4. We reform that into H2. H2 flows along the anode side, air along the cathode. You have O2 ion pass through, recombines into water and CO2. When we operate as an electrolyzer, instead of supplying with CH4, we supply with steam. So we supply steam to the electrolyzer, and then air, supply with electricity, and allows us to electrolyze water into oxygen and hydrogen very efficiently. So to Barry's point, one of the major benefits that we have, and we're new in the electrolyzer industry, but we're building our product off of years of an established SOFC product. So the modularity, the supply chain, the manufacturing processes are very mature. We have a monitoring infrastructure that we've established with our SOFC product. 3 facilities across the world where we monitor every installation 24 hours a day. We know exactly what's going on with every module that we have in the fleet. And then again, our modularity and scalability, we build in small building blocks, so we're able to deploy these very quickly. Our electrolyzer product allows us to use wind, solar, nuclear as inputs. We supply steam, and then and we produce hydrogen. We're generally 20 to 40% more efficient than low temp electrolyzers. So put your money where your mouth is. We've built a large-scale demonstrator, not as large as some of the ones you all talk about, but still large for us. A 4 megawatt SOEC installation was producing about 2.5 tons per day. We built this installation at Ames Research Center in Moffett Field, California. along with that, we've been working with the DOE, with Idaho National Labs. We have an installation there where they've been testing our solid oxide electrolyzer system, as well as hundreds of thousands of hours of individual stack testing, over 82,000 hours of module testing. Just a snapshot, a brief snapshot comparison of technologies. What we're looking at, the benefit of efficiency is really what drives the success of our product. That, along with our estimated learning rate, even though we're well established in SOFC, being that we've only been producing SOECs for a couple of years, we're learning very quickly ways to bring the cost down. So our learning rate for initial CapEx expenditure for our product is coming down very quickly. Again, our material availability, our supply chain is very robust. It's very similar to our SOFC product. So there's even, in some cases, the BOP is a little bit simpler than our SOFC product. There's other areas where we're able to reduce cost by reducing complexity, and so we're learning more and more as we go. And so it leads to a very low levelized cost of H2. And I'll hand it off to Charles.
Thanks, Brian. Good afternoon, everyone. So how does the product work, or what's the product architecture? So what you see here is a simplified architecture of how our electrolyzer system works. Basically, you have your inputs. You have your rectified AC to DC for the process. We do need some hydrogen supply initially to reform our cells at the start. Steam supply for the process, and then nitrogen supply for safety and changeover of modules, since it is modular. Within the box, as Brian and Barry talked about, is what we have experience with in our testing, right? But outside of that dotted line box is where we would like to collaborate, partner, et cetera, with our technology, because hydrogen collection, drying and compression, we come out at a low pressure, storage and distribution is something that we would look into. But we all know from this technology and PEM technology that the benefits are, if you pair our technology with clean energy, right, the output is just heat and water, that if you find a way to store it correctly, then you are eliminating material waste from more conventional storage, such as batteries, right? So that's what we're looking to do and the impact we're trying to make. So when you look at the hydrogen segment applications, right, there is a global shift, and we've had customers from Europe come to our facility in thinking of using fossil fuels for hydrogen production. But the issue is, right, cost around it, the ability to do these processes. And so if we don't have a way to make it a reality, right, we will have to turn back to the conventional methods because the demand will just be too high and we'll get stuck, right? And so that is our concern. That's why we're here talking to you all today. And the segments that you see bolded are the ones that Bloom is involved in, but it is not limited to those, but that's the ones that we are currently focused on supporting. So to put it a different way, you can see that how we view where hydrogen is being used in the processes. And due to the need for specialized materials, due to the need for specialized fuels, hydrogen demand since 1975 has tripled and is continuing to grow. And hydrogen supplied for fossil fuels constitute about 6% of natural gas usage, 2% of coal usage, which translates to about 830 tons of carbon emissions per year. And when you look at that, conversely, from electrolyzed hydrogen, we only support 1 to 3% of that, with the restrictions being, as I said before, the cost of the technology, and then also environmental concerns such as lack space and other environmental restrictions. So there's challenges, there's things that we're looking to do to accomplish. We're here as a partner to try to get this technology going, to continue to meet the charge. And we believe that, you know, to make the hydrogen economy a reality, it's going to take a coordinated and concerted effort. Thank you.
Questions?
With that, we'll take a few questions. Shunbo?
Yeah, glad to hear this because I thought I was the only SYC people in the room. Everybody actually, several years ago, when I had a DOE project, Bloom was my partner. That was the only DOE project Bloom was involved. Sorry. The question is, one of the slides you showed, you feed in methane to end site.
Yeah, it's
You
not.
directly feed in methane?
It's a more like a marketing slide. No, it's,
Oh.
it's reformed.
Okay.
We reform it prior to fuel cell. So we have a SMR.
Yes.
What do you feel like is the next big problem in overall system costs that you need to fix?
So as Charles kind of alluded to, for us, I think our ability to get the cost of actually producing hydrogen is achievable. It's what we call the BOP2. It's the next process of what do we do with that hydrogen. We're not in that business. That's not been part of what we've done in the
I'll add
past.
to that one. I'll add to that one. It's you know, our product cost rapidly comes down. The benefit of our products that we're highly modular, the drawback of our product is we're highly modular. So installation costs, right? Installation costs are always an issue. So we're working on ways to change our product so that it continues to be highly modular, yet the install is not. And so that's one of the big focuses that we're looking at now, is how to increase power density, how to reduce install costs, because that's a major cost all across the board.
I'm not that familiar with solid oxide, but what are your catalysts? Are you still using precious metals, or are you?
We don't use any precious metals.
No precious metals.
The electrolyte is like a YSC, yttrium, stabilized zirconia kind of base. We've departed from that a while back, so we have our own formulation. The inks are all proprietary, but there's no precious metals in any of them. And we have a well-established supply chain for all of those. So that's part of our what we've done to kind of secure our business is we have that from the ground to the customer.
And for the electrolyzers, that's consistent with what we've established for the fuel cell.
It's essentially, it's our same manufacturing process, it's our same inks, it's our same electrolyte. A combination of which we manufactured slightly different, but otherwise it's identical.
Mm-hmm.
One more question. I'm a Delaware resident, so I help support Bloom.
Thank you.
With the subsidy. But in the wording, when you first formed the corporation here, there was a term like renewable natural gas. What is that? In order to get funding. That was a term that was used.
I don't know, I didn't create the term, and that predated me, so I'm not sure how.
But you're using just natural gas.
We use natural gas. We have a product that takes direct biogas, so biomethane. We use directed biogas. We have a pure H2 product. We run it off alcohol. I mean,
we have all of those in service making as well as a pretty well developed marine product, right? So we'll be able to.
You know, I bet that meant gas off of like landfills and farms. I mean,
yeah,
that's what it
it
meant.
might be.
yeah.
Yeah, and we do that. We have units running off of landfills now, and we have units running off of dairy waste biogas.
We started calling that biomethane. Later on, we learned a valuable lesson. It's mostly CO2, and you've got to get
probably right.
All right, we have time for one more question.
If you're at really high operating temperatures, does this eliminate certain parts of the world where you can deploy this technology?
No, we've had no restrictions on any of the environmental. The temperatures that come out after we recycle the heat, and that's part of the efficiency of the unit. So we maintain the heat, so that heat stays. We're an always-on product. We're not cycling or backup. So the thing hits 800 degrees Celsius, it stays there. That's where it likes to live. The heat coming off of it is around 140 Fahrenheit, something like that. It's not too hot.
Yeah, and in SOFC applications, not at all, because a lot of times we're actually asked to recover that heat for combined heat and power solutions, and we haven't experienced any of that for SOEC yet.
All right. Let's thank our
Thank you. I'll try not taking anything.
All right, for our last talk of the day, I would like to turn it over to Yushan Yan. So I'm surprised you don't have like 3 sheets of papers here. I always joke with Yushan that I don't think he could get any more hats. But so Yushan is the Henry B. DuPont Chair of Chemical and Biomolecular Engineering and the founding director of the Center for Clean Hydrogen at the University of Delaware. He's the founder and CEO of Versogen, a co-founder of RepAir, and board of director for Mach 2. And with that, I'm going to turn it over to Yushan.
Thank you, team. First, I'd like to thank the National Academy of Engineering for giving us the opportunity to host the meeting. And I think there's a great benefit to be the last speaker. And for a very focused conference, maybe I don't need to talk. Maybe I don't have the time to talk. And I think I got both. And I'll try to be efficient like my colleague A.J. Prasad. The topic I'm going to talk about is my own journey from laboratory research to the commercialization. And there's a particular line of work that is hydroxide exchange membrane, or AEM. There's another name. So you're going to see a mixture of that in my presentation intentionally. As Tim mentioned, I'm the founder and CEO of Versogen. This is a UD spin-off. It has 40 plus employees, its own building, about a mile away from here. This is my standard conflict of interest disclosure. So you're going to see a mixture of slides. So the first one, I'm going to start with a Versogen slides. The challenge has been outlined very clearly today by many of the previous speakers. We need to get down to $1 per kilogram. And the approach we've been taking is this AEM green hydrogen, anion exchange membrane electrolyzers. We have heard about PEM, we have heard about alkaline, we have heard about solid oxide. So we're taking a very different approach, AEM. And by the way, I've been working on hydrogen for the past 26 years now, with the last 20 years solely focused on this AEM platform. So I'm a very single play researcher. The reason we want to do either AEM or HEM is if you look at the left-hand side, the liquid alkaline electrolyzer has been there for 100 years. It used potassium hydroxide as the electrolyte, the separator between the anode and cathode. And the benefit of this technology is it uses very inexpensive catalysts like nickel, use very inexpensive plates like stainless steel. And then about half a century ago, this PEM electrolyzer came along. And this technology has benefit, like Andrew already outlined in detail. It has high performance. You can get a lot of current density out of it. That means on a per unit material basis, you can get more hydrogen. It has this dynamic behavior to follow the electricity, either wind or solar. It can pressurize the hydrogen. And then AEM is the approach we've been taking. It basically combines all the advantages the other two technologies offer. And one way to imagine this, This is a strong child of two very powerful parents. So it really has all the benefit the other two technologies offer. That's why we've been very excited about this technology. I thought our friend, Plug, is in the audience, and I want to highlight, this is a picture I lifted off the Plug website. The point I want to make is stack is really at the center of the hydrogen plant from the engineering point of view. From cost point of view, there's a lot of other costs you have to spend in order for this technology to work. So stack is at the center of the system. And here is a exploded view of a stack. A stack has many, many cells. And if you look at each cell, for this particular one, to the left, I highlighted one single cell. Literally at the center, that's the membrane. So the point I want to make here is the membrane is at the center of a cell. And that is why we really need to work out this membrane in order for us to see success of this AEM or HEM technology. Otherwise, we won't see it. So the first successful proposal my research group wrote was 2006, supported by an internal University of California, Los Alamos joint program. It was small, but it was a good starting point. So over the years, we've been making very steady progress. So our first publication on quaternary phosphonium was 2009. Our first patent on pepper ion, this is the platform we've been scaling in 2016. And then we founded Versogen 2017, and 2019, the first publication came out. So this one gives you the detail, a little bit detail of the pepper ion. This is a brand new polymer that didn't exist before. It has an aromatic backbone with a pepperidinium cation as the functional group. So we need a positively charged cation group so that we can put hydroxide on the side to make this a hydroxide conductor. We have done a lot of work in this area. Let me just simply say this new polymer membrane is very conductive and very stable chemically and very stable, very strong mechanically. So this is a very good combination. And I was convinced there is a commercial opportunity for us. And that is why toward the end of 2017, we founded Versogen, and we've been doing scaling up ever since. So if you look at the picture on the left, used to be on the UD campus, we do synthesis at about 3 to 5 gram a batch. And now at Versogen, we're at a scale of 20 kilograms, more than that, a batch. And I personally learned a lot. And I'm claiming I'm a chemical engineer, but there are many moments I wondered if I was a chemical engineer, Not sure I was knowledgeable enough. So we have the membrane started with drop casting. You literally just pouring it into a Petri dish, and you get like 5 square centimeters. And now we're making the membrane row to row. We can make thousands of square meters, one trip, to do the membrane production. And if you look at the membrane, we have a capacity of a gigawatt per year using 40 micron membrane as a way of doing this correlation. So we're not capacity limited on the membrane anymore. We have 70 plus customers worldwide. As a small company, we actually have steady growing revenues, which is very nice. And we have multi-million-dollar contracts with our major customers. So this one is about our stack effort, we're not only doing membranes, we have decided to go down the value chain one more step to make stack. And our stack is a ground-up design. It is not a straight borrowing of the alkaline electrolyzer stack design. It's not a PEM electrolyzer stack design either. We felt pretty strongly we need to take on the challenge and do the design very specifically for our AEM membranes. And the design we did has built-in flexibility because we knew AEM is still at the front end of the innovation, and we're going to have suppliers evolving their technology. So what we wanted to do is design our stack in such a way, if our suppliers evolving their technology, we wouldn't be forced to back to the drawing board to change our design. And we have very low repeating distance, a very compact design inspired by automotive stack design. So this is our quick timeline about the stack development. Versogen has gone through Series A funding already. In the Series A funding, we have moved from a single cell, 5 square centimeter, to 100 kilowatt stack. So this has been very fast progress. And Series B, we're going to get the stack to a megawatt toward the end of this year, performance tested and durability tested by the end of 2025. And we intend to have a pilot plant for the limited manufacturing of the stack by the end of 2026. And then from there on, going for a gigawatt factory. Although we need the gigawatt factory, we need the pilot plant, but Versogen doesn't have to do it alone. So if you're interested in working together, let me know, or my colleagues, I think Baosu, at least Jim is still here. So now I want to spend a minute talking about Center for Clean Hydrogen. This is the idea that came to us maybe 3 years ago. Mostly, I think, started with a conversation I had with Tim Hopkins. I always felt Tim is a co-founder of the center. The funding partners are University of Delaware, the Chemours company, Plug Power, and NREL. So why did we want to have this center? The idea was actually quite simple. Our anticipation was many component companies are going to come into the hydrogen space. And most of them won't be able to justify to put down $30 million building, waiting for 3 years, because they don't know if their product is great or not yet. So we wanted to fill that gap. And so if you look at the bottom bullet, at the foundation of the center is the ability to test stack component and stack at scale, at megawatt scale. And so far, since we announced the center's formation, we have very, very positive feedback from the community. But once we have this very unique capability, you can imagine we can do our research in a way that is not easily available anywhere else. And we're going to be able to train chemical engineers, electrochemical engineers, I should say, in a way not easily available in other places. And we also can do entrepreneurship at a whole new level. Now I want to spend a minute to cover this hydrogen hub. As Sunita and others mentioned, there are 7 hydrogen hubs awarded last year. I think I've said this at other occasions. For me, I've been working on hydrogen for 26 years. I'll be just extremely happy to have one hydrogen hub anywhere in the country. And having one in my backyard, I still don't really have the right word to describe my excitement. And we were very lucky to be part of this hydrogen hub. I thought George Murphy, at least he was here. George is one of the collaborators I had in the time of writing proposals. It was a lot of meetings and a lot of writing and debating. So we were very glad to be part of that. And Versogen is part of that as well. So now I want to make some very bold claims. I want to say we really have a historic opportunity and perhaps an unparalleled ecosystem in Delaware. It's a small state. If you look at AEM technology, my group has been dedicating itself for a lot of things. We have about 20 people working there. And we do scaling up of the AEM technology at Versogen. Versogen has 40 plus people, its own building. And if you look at the Center for Clean Hydrogen, we can do the testing of component, of the stack at scale. That will be a benefit for all the companies out there. It doesn't have to be a Delaware company, doesn't even have to be a US company. And then if you look at the Mach 2 project, that's where we can do our first demonstration, do our learning. Once we get that done, I hope we can get a cost structure much more optimized. So now is my wild claim. I want to say Delaware is an undisputed capital of ion exchange membranes. Look, you know, we have PAM, we have AEM, and we have PAM reinforced, not reinforced, and there's more. And I want to say DE will become a capital of clean hydrogen with Air Liquide, Bloom Energy, and Versogen. And I apologize to my collaborators in southern New Jersey and southeast Pennsylvania. I'm an employee of UD. My Versogen is in Delaware, so that has to be the claim. And now I just want to show you the timeline again and the acknowledgement. As you can see, I'm a huge beneficiary of DOE support, and in particular, Upper E. So I've been very, very fortunate. And I want to thank all my student and postdocs and associate collaborators at both University of California, Riverside, which was my employer for 13 years, and University of Delaware, and Versogen. And with that, I'm done and happy to answer any questions. If there's a time, I don't want to be really between you and the reception. Thank you.
All right, any questions? Yes, please.
Yushan from DuPont. So first of all, great learning for me. I never worked on any of the technology, so I learned a lot about hydrogen. My question is, today my biggest learning is about reduction, the cost reduction. I haven't heard about efficiency. I have not heard about robustness enough. I mean, is the efficiency already high enough, or do we have the right tool to understand the robustness of various technologies?
Yeah, I think in the previous presentation by Barry, there is a list of efficiencies. In terms of efficiency, I think solid oxide is looking very good. And if you look at low temperature technology like our AEM, HEM, or flux PAM, we are working at a operating point that is having lower efficiency. But I want to go back to your first question, the cost of hydrogen. The way I'm framing it, it has three parts. One is the electricity cost, and that has to be right. We don't really control in here. And the second one is the materials cost of the stack itself. And that's where AEM is very exciting to me. And the third piece, that doesn't get discussed adequately, I would say, is the manufacturing. Kathy touched it a bit, but really that's a big deal. And that's very, very important for us when we design our stack, and we need to design with that manufacturing in mind so that we can do it at a lower cost at the right scale.
Great. Karen?
Dr. Young, you make some very bold claims, which I love. Is the governor of Delaware aware of this, and the senators and
One time I told him the tagline, he said he was going to borrow it to do his stump speech. So maybe I have one more slide to just let you look. Electrochemical engineering is going to be the frontier of chemical engineering or engineering. I've been saying that for a long time. And we published in 2014.
There has been enormous push these days on the air mobility, but I haven't heard much about any focus towards aviation.
I used to be an aerospace engineer before I became a faculty. So I used to work with Boeing, NASA quite a bit. I think there's quite a bit of effort in trying to get hydrogen applied to aviation. I think there's effort to get battery into that as well. But I admit I wasn't paying enough attention to those to comment very intelligently.
Any last questions? Yes.
How many patents do you have on paper ion?
We probably have 12 or 13 patents. The leading one is being nationalized in 13 countries and regions. I think we're like 2/3 through.
So you protected it some, so it can't be gotten around very easily with chemical.
Well, I wouldn't say it can be, circumvented, but we had a compositional matter patent, so it's a very strong. In terms of the infringement, an MR would tell whether the other party has our material or not. So we do have a strong protection. But I wouldn't try to convince anyone it's fully.
If you're a good lawyer, you're okay.
Yeah.
That's not a hat you're wearing? No.
I did a lot of IP negotiations, done a lot of fundraising negotiations. Some friends told me that I might have a future in the legal field because when I was representing Versogen, I didn't have money for big lawyers, and the other side, like 9 lawyers versus me.
All right, well, let's thank Yushan.